All right, everybody. So I think that what this video is going to be is we're going to be looking at the MIPS Lab 2. Now, having said that, I don't know. Let me see here. Let me open my downloads folder, probably. And if I say Java, Char, Mars, okay, cool. Um, so I'll open that up as well. And what we're going to be doing in this video is we're going to be looking at the zyBooks for MIPS. So this MIPS homework is due at the end of next week, December 12th. Oh, that's my Apple Card. I was trying to not look at that. I was trying to look at blah, the date, but you can't get the date there. You have to do this to get the date. And then it's up here somewhere. Aha. December 12th, next Friday. All right. So, what are we doing? Well, we're going to be looking at the zyBooks for MIPS. So if we open up the zyBooks for MIPS, we will go here. Now, while we're at it, I know that there's some people who have not been in lab, and so before we look at that, I'm just going to mention a couple of basics for MIPS. So you have to, if you want to do MIPS on your own, we need this Mars simulator, which there are things in the labs that will help you get started with that. But I'm going to create a new file here. And what we remember about MIPS is that there's a data section and there's a text section, and it doesn't matter which one goes first. So I can put text at the top if I want. I could put data at the top if I want. It doesn't really matter. And the text section is where you put your code goes here. And your data section is where we put basically variables that are going to be accessed in the code. So I say variables, but basically things we want in memory, which I guess are variables. So like we were doing things like putting strings here, right? Like if we want to make a message, I could call it message. That's just a name. Okay, so that's not a special type or anything. Message is just a name, so like I can call it message one. Um, you have to say what kind of thing is it. In this case, it's an ASCII Z, and it says here, store the string in the data segment and add null terminator. The null terminator is important. That's how the operating system knows it gets to the end of a string. Um, so if you type it without the Z, you get the wrong thing for us. So we want the Z. And then you put the message here, right? So we say like, hello world. So this is just a reminder of how MIPS works. So like you can put stuff up here that we might need to print, like message one, message two could be goodbye world. Um, we could save that somewhere. I'll just let that save, I guess, in my downloads. It doesn't matter. And then, we can put our code down here. And so the code is mostly going to be done with basic instructions. So we can have instructions like LI, LA. Those are load instructions. They start with L. LI is to load a number. LA is to load an address. So like if you want to print message one and message two, we need an address to where these things live. There's move instructions for moving things around. There's store instructions that start with S, but we're not using them yet. We'll see them in the zyBooks. Um, and in the second MIPS lab, we learned about jumping around, which involved a jump instruction. And then there were a bunch of branching instructions that started with B, like B and E for branch not equal, BEQ for branch equal. Oops. Um, BLT for branch less than, BGT for branch greater than, BGE for branch greater than or equal, BLE for branch less than or equal. So we have like instructions here. We also have syscalls, which is how we get everything done. And so this is just kind of a reminder of some stuff that we maybe know from lab. To print a message, we learned that you had to load an immediate. There were registers that have names, and one of the registers is called V0. And V0 is the one where we put, among other things, commands for syscalls. So syscall 4 is print a string. And so if we put a 4 into V0, that means we're trying to print a string. And then you have to put the thing you're trying to print, the string, into the right address. So you use LA, and into A0, we put the thing that we're trying to print. So I could print message 1 or message 2. So if I put message 1, then that puts the address for message 1 into A0. And this is you know, the string we want to print goes there. And then when we do a syscall, we should actually get our thing printed. So I just hit Command S to save this, and I'm gonna assemble, and it assembled correctly, it says. And then I can run it, and it says hello world. And if I go back up here to edit, I could change that to message 2, and I could run it again. So 2 steps, and it says goodbye world. So we have a basic functioning program here, and that's all we need to get started here with the zyBooks. Of course, we can just ignore, we don't have to write real code when we're doing zyBooks. I just kind of want that there for reference. Now, 9.1, right, they're going to explain the concept of a processor. So, they're going to say, like, you have a processor, you can run a program. The program is the instructions, the list of instructions that you're going to run. The processor executes one instruction at a time, proceeding to the next one. Here they're written in words, but they are using like words to describe the instructions, but they're using the proper variable names, or sorry, register names. So T0, T1, T5 are all register names. And so this is the first section on this, so there's not a lot of information in zyBooks yet. But keep in mind that if you go back to the course webpage and you look at my MIPS reference charts page that I made for you guys, it's got tabs up here. And like if I click on MIPS registers, for example, you get a list of all of the registers that MIPS has. There's 32 of them, and they're all listed here. A lot of them have similar names, so they're grouped. And you can see what they're for. So like if you look over in the zyBooks, you'll see like it says T0, T1, T5, T4, T3. You look back over here and you see the registers that are T, and it says those are the temporary registers. And those are the ones that you're allowed to do whatever you want with. And so that's what they're using over here or over here. So it makes sense. Again, we're just in the first section here of MIPS. So what they're saying here is they're talking about instructions that load stuff from memory. So they're saying that these are your list of instructions in memory. They're calling that IM, instruction memory. And then they have your data memory over here. And they're saying in the data memory, we have like a 20, a 40, and a 60. Those are the numbers that are stored. And the numbers on the left here are like memory locations. So like memory location 5000, 5001, 5002, 5003, 5004. So your registers are over here. And notice that they've got the registers T0 through T6. There's 32 of them, but they're just drawing some of them. They do have a 0 register. Interesting. We do in MIPS in general. So load T0 with DM5001. So they're saying DM5001 is over here. So you find the 5001. The value in there is a 20. So we're getting the 20 and we're putting the 20 into T0. So you can see that they put the 20 down there. And then they have load T1 with DM5002. 5002 is here. You get the 40. You put the 40 into T1. It goes there. Then add, you put the register for the destination all the way on the left. This is not a proper MIPS command, but um, just in general in MIPS, you put the destination on the left. Um, and then these are the two things being added. So we're adding T0 and T1, which are 20 and 40, you see, and we're putting the result in T5. So 20 plus 40 is 60, and we're going to put the result in T5. So it puts it here in T5, but this is all the register, which is in registers, which are inside the CPU. So the registers are like memory locations, but they're built into the CPU. They're not your main memory. So after they added these numbers and they put the answer in T5 down here, then the next command, the one they highlighted here, it says store T5 to DM5005. So we're going to take this 60 that's in T5 and we're going to move it to this memory location 5005. And the 60 ends up down here. Then what do? Load T4 with DM5015, which they haven't done yet. And so they haven't done instructions 4 and 5 here. But if they do, it says load T4 with DM5015. What does that do? I have no idea because we only see this much, right? We don't see 5015. It would be, you know, down lower. All right. So anyway, we looked at that. So referred to the above animation. I didn't watch the animation. What is the value in 5002? So you go up here. 5002 is 40. What is the value in T1 after load T1? So after you do this, right? Load T1 with 5002. So you're getting the 40 and you're putting it in T1. So what is the value in T1 after you do that? 40. The first add instruction adds T0 and T1 and puts the result where? So this is the first add instruction. So it adds up T0 and T1. It puts the result in T5. How many executed instructions copy data from the data memory to the register during the animation? Well, I think the animation must go 0 to 3. Do you think it goes all the way? Um, well, if it only goes from 0 to 3, then there's 2 load instructions. Um, but then there's another one if we go past that. So it's either 2 or 3, depending. The only way to know for sure is to watch the animation, but I'm not. How many executed instructions use the ALU? ALU is for math. So ALU is doing adds and subtracts and multiplies, that kind of thing. So this is an ALU instruction, and this is an ALU instruction. But if we stop at instruction 3, then I think this is the only one. How many total instructions? Well, again, I think if they stop at 3, it's 1, 2, 3, 4. Yeah. The CPU contains a register file and what other component? Look at the picture. CPU right here. What does it contain? Register file, ALU. So they would just want you to look at that. A typical register file has 1G or more registers. No, MIPS has 32. So not a giga register. We have 32. False. 1G or billion is more appropriate for memory. Yeah, so the amount of registers that are on your CPU varies by the CPU and the CPU architecture. Modern CPUs, have a lot more, but they use a lot of tricks as well. So like to make CPUs faster, sometimes what they do is the original specification that was made, in the dawn of time said that there were 32 registers. But they wanted to make the CPU faster and faster and faster, right? So maybe they add more registers, but the specification only has 32. So how do you add more registers and still follow the specification? Well, what they'll do is you could have like extra registers that exist, um, but the CPU uses them internally to kind of keep the results of earlier computations, and it kind of moves them around silently. And from the outside world, it looks like there's 32 registers, but internally to the CPU, there actually there's more, and they just move stuff around behind the scenes without you seeing it in order to speed up certain operations. But anyway, 32 is a normal amount for MIPS. That's what we get. Instruction order. So the instructions happen in order. Um, Complete the following instruction sequence to add values in registers T0 and T1 and store the result. Uh, okay. Add values in T0 and T1. So this right here moves a value from T6 into DM 5007. So whatever the thing that we're moving needs to be in T6, right? So when you look at this, um, this one is going to put the result in T6, and this one's going to put the result in T6. So one of these is correct. This one adds T1 and T0. This one adds T2 and T0. So we're supposed to be adding T0 and T1. So T0 and T1, put the result in T6, and then T6 can be moved to the memory address. All right. Um, let's just keep scrolling. I feel like this is going really slow. If you wanted to add three numbers, how would you do it? Well, there's no instruction to add three numbers. So in assembly language, you have to do it in two steps. So, um, so for example, what this does, this one here, we're trying to add T1, T2, T3. So this one adds T1 and T2 and stores the result in T3. That's bad because first of all, whatever was originally in T3 is now gone. So we won't be able to add it. And then we do T3 plus T3, which will double the result. So actually, this top calculation here, um, it adds T1 and T2 and then doubles it. So that's completely wrong. So I mean, it must be this one. This one adds T1 and T2, stores the result in T4, and then does T4 plus T3. That's correct, right? Because T4 is T1 plus T2. So T4 is T1 plus T2. Put the result in T3 or add T3 and then put the result in T0. So this one adds T1 and T2 and T3. So certainly correct. Kind of the same thing here. If you wanted to add T1, T2, T3, T4, how would you do it? This does T1 and T2. All right, puts it in T4. Now we've lost the original T4, so this is wrong. What does this one do? Adds T1 and T2, puts it somewhere. Adds T3 and T4, puts it somewhere. So half of your answer is in T5 and half of your answer is in T6, and then it adds T5 and T6 and puts the answer in T0, right? So they're trying to get across here that you're going to take, like, to do a calculation like this, it actually is taking you three different add instructions in order to um, do the calculation. So like the next problem which says T4 equals T3 plus T2 plus T1 plus T0 can be completed in two instructions. I don't see how. It took us three up here. And I don't really see a way to make it work more efficiently. All right. Blah, blah, blah. If you do T1 plus T2 stored in T2, this is like basic programming stuff, so you'll be easy. This is easy, right? T1 equals 5, T2 equals 3. So if you do T1 plus T2, you get 5 plus 3, which is 8. So this side is 8, and we're going to put an 8 in T2. All right, so we're just following along. Um, Here, if you started with these, maybe we could, where is text edit? If you had these to start with, right, 2, 5, and 4, and you look at this, if you do T0 equals T0 plus T1, that's T0 plus T1, that's 2 plus 5, which is 7, and then you store the result in T0. So we're replacing T0 with 7. And then the next line does T0 plus T2. So now T0 is 7, T2 is 4, so 7 plus 4 is 11, and 11 gets put into T0. So 11. And then the question is, what is in T0? It's 11. So you just do the instructions in order, and it, works the same as any other programming language works here. Um, all right. Okay, so they're showing you how they represent this. They're saying if they put a grayed out number here, then they're saying that this was the previous value that was in T3. So the current value in T3 is 75, but the previous value was 70. Um, so it's good to know. That's just how zyBooks is going to draw it. They start talking about MIPS. MIPS is the most popular processor in commercial products today. Not today. Today, it's probably ARM. Um, but when this was written, it could have been true, but I'll say false. Um, the register file in MIPS has 32 registers. True. The register file in MIPS ZY has 32 registers. Mm, I didn't read. Let's say true. Oh no. We only have these. Okay. This is it for us. So if we go over to the Mars simulator, we have 32. If we are in zyBooks, we got T0 through T6, which is 7, and then the 0 register, which, as shown here, there's actually a register called 0 that just is always 0. Um, Apparently, that's important enough, comes up enough that it's included in a lot of processors. All right, so then they're going to start teaching us um, some instructions. Now, it's interesting because these instructions are not um, ones that we use in the labs very often, because in the labs, um, we're just mostly not using memory. We're mostly just loading stuff into the registers and dealing with it there. So that's part of the reason why I've assigned these sections, is because, we can do different things in the lab versus in the zyBooks. So the two instructions they want to teach us here are load word, W, load word. So a load instruction copies data uh, from memory to the register. Okay. And then the store instruction is going to do the opposite direction. So load is memory to register, store is register to memory. And the way you write them is LW for load word, the register where you want to put the answer, and then something like this, where this is indicating this register has a memory location in it. Um, so we're going to go to this register, get the memory location 2020, and then we're going to try to read from 2020. So what's the question here? What is the memory address being accessed? 2020. Um, so you have to kind of, how should I put this? It's multiple steps to think about this. So like, given this instruction, we're loading into T3. So this is the destination. What? Well, this says 0 T6. So you have to go to T6. So you go to T6 down here. The number is 5200. So we're loading whatever is in 5200. So you go to T6, it's 5200. You go over here to find 5200, it's right at top. And then the answer is a 24. So we're getting a 24 and we're putting the result in T3. So it's two steps. You have to go to T6 to get the memory address, and then go to the memory address to get the actual value. Okay. So given the following register file, we want to load into T2 the data at 5012. So 5012 I see is down here in T6. So you'd have to put a T6 there. All right. Assuming T5, oh, T5 holds 6000. It doesn't. Okay, that's a different question. Oh. Assuming T5 holds 6000, write a load instruction that loads register T4 with the data at 6000. So load word, and then the destination comes next. So when it says loads register T4, the T4 comes now. And then with the data at memory address 6000, well, the 6000 is actually in T5. So you put a 0 parentheses T5. So which register is T4, like which place gets T4 and which place gets T5 is what they wanted to check. Okay. Store works the opposite way. So we're copying from the register to the memory, but the syntax looks the same, like the order is the same. So when you do a store, now we're not putting something into T6. We're taking what was in T6 and it's going over here to the memory address specified in T0. So assuming T6 holds 600, so we're taking a 600 and we're storing it somewhere, and T0 holds 5008. What is the memory address? So this is the value that we're going to store, and this is the memory address. So the 5008 is the memory address. Okay. Given T2 holds 6200, so that's going to be the memory address. T3 holds 536, so this is 536. And T4 stores 616. There's no T4 down here at all, so we don't care what's in T4. It says what value is stored. Okay, so the memory location is 6200 because the 6200 is here. T3 has the number 536. So 536 is the number that's going to go into memory. Cool. Given the following register file, complete the store instruction to store T2's value into 5000. So first of all, T4, you see T4 here is 5000. So that part's already done. So memory address 5000 is already written for us. And we want to store register T2's value into memory. So you just put T2 here. All right. So they explain the syntax again. Um, you can try these out here. The problem is like what are your memory addresses? So like if I run this, I'm going to run it, assemble it. Um, and you see your addresses are like here. So these are your memory type addresses. Um, so like if you wanted to store something, maybe I could, can I copy? No? Oh, well, we will maybe deal with that later. But you can use these instructions in Mars. It's just that the memory locations are not going to be 5,000. They're going to be bigger numbers. All right, try this. Compute T3 equals DM77D. So the 7700 is here in T2. So you'd want this to be T2, which it is. And we want to put the result into T3. So we have to change this to T3. So this is the destination. And we have to get the instruction right as well. So loads from memory to the register. So load is correct. Cool. Let's skip to number 3. Ooh, what are we doing? If you want to move, look what they're doing. So in memory, they have a 5 here, and they want to take that 5 and they want to copy it over here. But there's not actually a copy from memory to memory command. So in order to do this, I have to take this 5 and stick it into a register. I'll stick it into this register. So I need to put the 5 into T4 first. I'm putting it in T4 because that one's not being used for anything. So to get the 5 into T0, what we got to do is the destination is going to be T4. So T4. And then in order to get the 5 is in location 6912. 6912 is in register T5. So you have to pick T5 here. And then we're loading to a register, so we want that to be load. So look at this top command now. The memory location is T5, which is 6912, so that's here. So we're going to get the 5 here. And then the destination is T4, so we're going to move the 5 over here to this highlighted 0. Boom. All right. Now, once this number is now 5, right? So what we've got right now is that T3 was 60, what the heck? 69, 12, no, 20. And we had T4, which started out 0, and we had T5, which started out 69, 12. And then in your memory, you had 69, 12 is 5, and we had 69, 20 was 0. And the point is we're trying to copy the 6912 value into the 6920, which means copy the 5 to the 0. All right, so this top command, what we did is it goes to T5, which is 6912, comes down to 6912, gets the 5, and then that is stored in T4. So we're going to replace the 0 with a 5. Now that we have the 5 here, we want to take this 5 in T4 and we want to copy it to 6920. So we want this to be T4 again, because T4 is where we put the 5. But we want the result to go into 6920, and 6920 is in T3, so this should be T3. But it shouldn't be a load, it should be a store, because we're copying it to the memory location. And then the result is that the 5 will get copied into that 0. Cool. We'll do a little bit more. Memory alignment, Indianness. So in memory alignment, when you have a sequence of bits, right? Actually, we're talking about memory alignment first. I was going to talk about Indianness first. Um, all right. Particular memory may store a sequence of 32-bit wide words. One might assume addresses for each word would increment by 1, like 0, 1, 2, 3, 4, 5. However, each byte in a word can be addressed individually. Thus, addresses for each word increment by 4, right? So basically, right, your memory addresses, since memory locations are by byte here, um, but a word is a 32-bit value, is 32 bits, right? If you're storing words to store words, we need to like count by fours, basically, right? So your first word, if you're storing your first word, which is a 32-bit value, could be just made up numbers at, let's say, memory 0, 0, 0, 0. Your second word, right, would be at 0, 0, 0, 4, because the first word takes up 4 bytes. So that's 0, 1, 2, and 3. So that's what they're trying to show you there is that this is 32 bits wide, but each one is counting by one. So your first word is at address 0, your second word is at address 4, your third word is at address 8, and so on. So multiples of 8. And what a lot of computer platforms do is either you're required to, or if you're not required to, you're still strongly encouraged to align everything to fours. So we're storing 32 bits at a time here, but even if we only had 16 bits to store, you might only be using like this one and this one. You'd put something here and then here, and then the next thing you store might go in the next row, and then this memory would be wasted over here. Um, Sometimes that's the way it works. Just depends on the memory layout and requirements of the platform. So anyway, they're saying um, 4 groups of 8. So we are counting like these are not counting rows. These are counting bytes. So this is bytes 0, 0, 1, 2, and 3 down a row, 4, 5, 6, 7 down a row, 8, 9, 10, 11. I'm saying too much. The word addresses increment by 4 because each one is 4 bytes. How many bytes exist per word? 4 bytes. That's what we just said. Each word is 32 bits. How many byte addresses exist for one word? That's depends on how they're counting them, right? They said 0, 1, 2, and 3 up here, right? So you could say 1, 2, like 4, right? But they say how many byte addresses. I think the point that they're trying to make is that word addresses increment by 4. So, oh, one word. Yeah, so 4. One word is 4 bytes, and so there are separate addresses for each of those bytes. What are the byte addresses for the word starting at 12? Well, the word starting at 12 is 12, and then the next byte is 13, and the next byte is 14, and the next byte is 15. Is storing a byte into address 15 allowed? Again, that depends on the platform, so we have to read up here to find out. Um, One might assume each byte in a word can be addressed individually. Okay. Storing a byte into address 15 allowed? I guess so. Is storing a word into address 15 allowed? No, because address 15 is at the end here. You can't fit four bytes here, and they're not going to allow you to put the first byte here and the other 3 down here because that would be unaligned. So everything has to start. If you're putting 32 bits in, you need to start all the way on the left. So you need to start at a multiple of 4. If you're putting 1 byte in, they say, yes, you can put a byte here because the byte fits. You can't put a word here because the word is 4 bytes. So 1 would have to be here and then 3 down here, and that's not allowed. A programmer wishes to load the last word of memory shown in the animation. What's the animation? Are they talking about 8? 8? Um, what? What address should be used in the load word instruction? 8? What is the address of the last word? I don't know. I didn't read. I didn't watch the animation. Go. Oh, please. Okay, so byte instructions can load one byte at a time. Word instruction loads an entire word at a time. It says word instructions load must be aligned, multiples of four only. So you can't load a word at one. What's it say? What address should be used in the load word instruction? What address is of the last word? Isn't it 8? Isn't that the 8? Do they mean 20? Oh, okay. Well, I thought they meant 8 because that's the last thing they put something in, but they actually meant 20 because it was the last one in the picture. All right. Uh, Big Indian versus Little Indian. This has actually been relevant because, like, if we do x86 Indianness, x86 is Little Indian. ARM Indianness. ARM processors are Little Indian by default, but they can also be configured to operate in Big Indian mode. Hmm. MIPS is either Big Indian or Little Indian. Is Mars MIPS Big or Little Indian? Newer versions support both. Cool. All right. So what is Indianness? So it varies based on the processor architecture. We know that because I was just looking up processor architectures. Indianness refers to whether bytes are ordered starting with the most significant byte first or the least significant byte first. So if you have a number, I guess this is the number. Um, so this is a 32-bit value, right? 8 zeros, and then this is just a particular value, so you don't need to pay attention to the exact numbers. But like zeros, zeros, ones, 0, 0, 0, 1, 1, 0, 0, 0, bunch of ones, right? How do you store that in memory? On Little Indian, it's the opposite order from what you see here. So you put the zeros all the way on the right, and then the second byte here is third here. The second, third here is second here, and last is first in Little Indian. But in Big Indian, then it's the opposite way. So this order is the way that it's written. Um, why? That's just the way the computers were designed to work. So that's just it. So Indianness only impacts the ordering of the bytes. The bits within the byte remain the same. Yeah. Yeah. Sometimes you'll look in, if you look inside a binary file, and you'll see like words, but with like two letters reversed, right? And it'll be because of this, right? They're putting the bytes in opposite orders, for example. Programmers usually need not be concerned with Indianness unless using byte level operations within a word, which is rare. Yeah, so if you write code like in C or C++, uh, and you're not doing something really low level, you don't care. The computer handles it however it wants to, right? Because you're not concerned with how the bytes are stored in memory. You're just concerned that they are stored and that they're going to be there when you need them later. So that's how that is. So let's see. Binary number is stored in word 20, Big Indian. So you just look at Big Indian. So which one was Big Indian? So here, the way the number was here is the way the number appears here. So Big Indian didn't change it. So zeros first, and then the zeros and ones, and then the all ones, and then last one. Little Indian. So now it's going to be the opposite order. So the zeros are first here, but that's going to be last. Uh, you know, 1, 1, 1, 1, 1, and then a bunch of zeros was last. So that'll be first. Then the second one here should be third, and the third one here should be second, right? Just the opposite order. Little Indian processors are faster. No, you don't. There's no difference in speed. Programmers spend much time and effort focusing on Indianness. No, unless you're writing low-level code that needs to run on CPUs that are both, then you have to like check which Indianness your processor is at the beginning of your code, and then do everything the right way. And so you have to write it both ways. In Little Indian format becomes blah blah blah. No, the bytes get rearranged, but like the bits inside of the byte stay the same. The bits inside the byte don't change. All right, cool. Um, we'll do a little bit of this and then we'll have to stop. We do a bunch of this in the labs, right? Add instructions. So I'm not going to talk about this too much. We already know about add immediate. This is adding a 4 to T0 and storing the result in T1. This is adding a -10, which is, of course, subtraction, but you can still add a negative. Uh, Adding -10 to T2, storing the result in T3. Cool. I'm skipping down to activities. Um, cool. Start. How do you do this? Add immediate. T0 is the register. So you go T0 plus 6. Um, what? What? Oh, we're doing regular add instruction now. So this should, I do not like this. So like add immediate is for when you have a register plus a constant, and add is for when you have three registers. And I feel like in this, they're giving you two registers here and then a place to type a number. I mean, the 6 must go here, but this is not being used then, I think. See, they want add I T0. Oh, never mind. My brain is broken. My brain is broken. Ignore everything I just said. We're gonna actually do this right now. Um, my brain was thinking there was three registers and there was only two written. Okay, how do you do this? Add immediate. The destination comes first, so T2. We're adding T3, so you put a T3, and we're adding 6, so you put a 6. Why was I confused about this before? Nobody knows. Next. T2 equals T4 plus T3. Now we're not adding an immediate, we're adding two registers. So if it's two registers, we want regular add instruction. And then the result comes first, so T2, and then T4, T3. So you just change it to T4, T3. Easy. How do you do this? Well, now to add three values together, you have to break it apart into two calculations. So there's more than one way to do this. But what I would do is, let's say into T1, let's do the first part. So let's add T3 and T0. So you go T3, T0. So T3 and T0 go into T1. So we've already added T3 and T0. The part we still need to do is T2. So in your next add instruction, we're going to put our result into T1 again. We're going to add T1, which is where I stuck the previous result, and T2. So the first line adds the T3 and T0. And the second line takes the result, which is going to be in T1, and adds the T2, which I do here. All right. T3 plus T2 plus 2. So again, you can do this with two calculations. It's going to be different ways to do this, but into T1, I'm going to put T3 plus T2, T3, T2. So I've done this much. Now I need to add 2 to the result. So the result is already in T1. So into T1, I'm going to put T1, but I'm going to add 2. So I'm going to change this to add immediate and put a 2. So that'll add a 2 to what was already in T1. All right. So we're going to stop here for time, but the next section is going to be on comments. You use # for comments. Pretty straightforward, right? All right. So I'll talk to you guys later. There will be at least one more video covering this stuff. But for now, we're done. I'll talk to you guys later. Well, as soon as I figure out how to end my video.